Okay, welcome back. So up until now we've been dealing with a bit of a narrow view over the kind of problems we're trying to solve, and we haven't really discussed that. So as now we've reached the A-star algorithm, we're starting to expand our horizons, right, in terms of how we're going to solve more substantially complicated problems moving forward, how we're going to augment the algorithms we've already seen towards these kind of domains and towards these characteristics, and towards these types of problems. Well, I think it's a good time then to take a step back and to establish the formal standard terminology for how we're going to describe together the characteristics of the types of task environments that we're going to be solving. So this list is not exhaustive. Language is evolving. Problems are the types of problems people are interested in are evolving. But these seven criteria here, I think, is extremely standard in a lot of the AI textbooks and ways we discuss these kinds of problems. And it's really important to be able to identify each of these kind of characteristics so that we can know when we're trying to discuss and compare two different algorithms, well, are they even solving the same problem? What are kind of things we're interested in solving as well? And how can we reason about things differently? In terms of that discussion then, so I'm going to go through and define each of these types of characteristics, and at the end we're going to jump across over here to the right where I have an example set up for the game of Tetris, and we're then going to talk about the characteristics that match the game of Tetris to kind of give you a grounded example of the things we're talking about. Okay, so number one here we have is fully versus partially observable. Why did I write it as the only one that isn't verse? No reason whatsoever. I'm just realizing that now. So what we mean by a problem being fully observable means that we are able to see you can see the entire problem. In a grid world, for example, a fully observable controller might mean one that is like up in the air, right? It has a bird's eye view of the entire problem. It can see everything coming. It's kind of like a game of chess, right? Like chess is fully observable. I can see all the pieces. I can see the entire board. You as the agent are some form of all-seeing controller. By partially observable, we just mean the opposite. You can't see everything, right? So some aspect of the problem is obscured from your view. You're not able to observe it. So this is, I think, much more common, right? Oftentimes you have a robot or an agent or a player and you're dropped in some form of environment and you're meant to reason over and make decisions to interact with the world. Well, in those kind of situations, you have some form of narrow, limited vision, perhaps, or you're only presented partial information about what is upcoming, right? And so you can only make decisions based on the things that you can directly observe right now, and hopefully reason about things that you've already observed in the past as well, and maybe what you predict in the future, right? This is kind of entering into this idea of these rational agents. But yeah, so partial and fully and partial observability is really just referring to what you can see in the world, right? What you can observe. Now, I do want to then jump actually down to 6 then to discuss known versus unknown, because I think that's often confused with fully and partially observable. What we mean by a task environment being known is that we are aware, we understand the rules of the world, right? Like the rules, the actions, and as well the effects of your actions. So the chess example, I think, is also good, right? Chess is a known environment. I know explicitly what happens when I make any move or when I go to move any piece. An unknown environment is one that you don't know all the rules. So your agent is going to have to essentially learn or build a model or of an understanding of how they can interact with the world and what happens when they interact with the world. So especially in pathfinding, we're usually dealing with known domains. We know the movements we can do, we know the environments, and then unknown environments are probably much more alike the types of problems you'd solve using machine learning approaches, right? These kind of reinforcement learning agents to try to interact with the world, create their own worldview, and then move forward and hopefully improve their performance towards some form of task measure. So partially and fully observable is how much of the world I can see. Can I observe everything? Known versus unknown is instead, do I know the rules? How I can interact with the world? Okay, so then we'll jump up to single and multi-agent. This one's extremely easy, obviously. It's just whether or not, when you're considering the problem, am I the single agent, I'm just making my own moves, or am I tasked with actually trying to coordinate a team, right? There could be multiple agents in the environment that you're controlling. Now, what I want to note, right, is in a pathfinding example, if you're Mario, right, and you're tasked with playing a game and dodging all the Koopas, the Koopa Troopers are not agents, right? We're describing an agent as an agent that you are able to control, right? So in this situation, this would not be a multi-agent problem. You are one agent, which is Mario, and the others are what we'd be calling obstacles. They are dynamic obstacles, they're moving, but they are not a controllable unit. Multi-agent problems are separate, right? Because it's, hey, I'm tasked with making decisions for 2 different entities, or 3 different entities, n different entities. And that introduces complexity into the problem that way. Okay, so then we have whether an environment is dynamic or static. I kind of just used the word dynamic there when I was talking about the Koopa Troopers. Well, dynamic just means that things are changing in the world while I'm planning, okay? So it's like moving obstacles, but it doesn't have to be that. It can be anything where essentially the environment is almost like online, but things can change. So dynamic problems are substantially harder than static. These are the types of problems where, say I'm a UAV, I'm tasked with planning navigating a path from A to B, right? But while I'm now thinking and trying to generate a path, things can change in the environment when I go to execute that path and while I'm still planning. These are dynamic situations, right? And then you would try to go execute your path, and it's really interleaving the planning and execution a bit more in these kind of environments. So you would need to continually adjust your worldview and make new decisions based on information you see. Right, so in a pathfinding example, maybe you plan a path, but then the path you planned, a door closed now, or a door opened, and these changes things about the way we've already reasoned about the world, right? Up until now, we've mostly been discussing static problems. Static problems just mean that you can spend as much time planning as you want, and then the moment you go to execute your plan, nothing's changed, right? It is static. It is unchanging. Okay. So then let's move on to deterministic and stochastic. So I think this can often be confused by students with dynamic. So they're not the same thing at all. Deterministic is talking about whether the outcomes of our actions are deterministic, or stochastic means there's a random chance to it. There's a probability involved, right? So a deterministic world is one where I choose to pass the ball from Messi to Suarez, and that happens every time. It's a world where I choose to go north and I move north, right? Stochastic worlds are often involved in like real world robotics. We enter these world of like Markov decision processes and trying to reason over probability distributions. These are, again, much harder problems because there's uncertainty built into the world. When I tell my robot to go north, well, maybe there's only an 80% chance it actually goes north, and then there's a 10% chance on either end that it goes either left or right. So these worlds then would be stochastic. When I execute an action, I'm actually not entirely sure what state I will transition to. So again, we have mostly been dealing with deterministic worlds, and this will match the kind of problem you're trying to solve. Okay, so discrete and continuous problems, this one's, I think, very easy. It just means whether or not the world, your states, are discrete. Is it a standard 0, 0, xy to 1, 1, xy, right? Or is it continuous? Do I have to include essentially the infinite number range between? So obviously the real world is kind of like this continuous thing. Oftentimes we're able to abstract it pretty easily. Just move in set, like there's some minimum distance that you can move and reason over, and that would make a problem discrete. So this one particularly kind of relates then to how you're framing the problem. Continuousness comes into play for things not only, so the spatial, can I move any distance forward? Then there's temporal, so is my time horizon continuous or is it in discrete time steps? Discrete time steps would be something like a game of Tetris, right? Where it's like you're a video game. Time literally steps in specific increments as opposed to solving an online problem where time's actually ticking. As a real player, right? Your time is constantly ticking. But then the third one I think is often forgot. So there is space, time, and also things like angle, right? So oftentimes our pathfinding algorithms, we've been talking about like these diagonals, right? Where you're doing just like a 45-degree angle. These movements are exciting and they make the problem harder. They make the branching factor larger. But problems with continuous any angle pathfinding, well, that is substantially faster. But there are really exciting algorithms that do handle these and can efficiently reason over these kind of any angle worlds. So oftentimes like discrete and continuous, this is just describing essentially like the state space and how you interact with the world. Continuous problems are also substantially harder. So I've already done known and unknown. So the last one then is episodic versus sequential. I think this is the most confusing easily of these terminology. Again, like, you know, terminology as well is always like, there's always a vagueness built in. You want these terms to be like explicitly deterministic. You want these terms to be explicit and concrete. And these are, but I think people get quite confused here because it's revolving now around the way we frame and view problems. And then maybe you can enter in asterisks in every way you discuss them. Episodic means essentially that when you solve a task, you're just solving a single episode of a task, right? The action I do now, the problem I'm given right now, has no impact on my future moves, my future plans. I'm reasoning, I'm an agent reasoning in an environment that is episodic. I'm making a bunch of decisions that are unrelated. The opposite of this is sequential decision making. So these are decisions, right, where essentially what I've done so far is going to impact my future path. Ordering of moves matters. This is things like navigation problems, pathfinding. These are sequential decision making processes. Essentially, the actions you do impact your future position, right? So you're solving a series of problems, a series of steps, as opposed to individual episodes. This is where it gets a little bit dicey, as I'll discuss then in the game of Tetris, because you can start to view the problem as either based on the way you frame it. Okay, so without further ado, let's jump across over to Tetris and discuss its characteristics. So is Tetris fully or partially observable? Note there's going to be a whole lot of asterisks in these, right? Because again, it depends on the version of Tetris you're playing, the implementation of Tetris, how you view the problem, all of this, how you go about solving the problem. So I think Tetris is, this is definitely one with an asterisk. And it also depends on whether we call it episodic and sequential or not. So I'll kind of do these at the same time. Some people view Tetris as episodic. I'm writing an agent that, just given a screenshot of a game, make the best decision. Okay, so in that sense, it's like you're solving individual episodes and they don't connect together. I think the more common version of this is like it is a sequential decision, right? Because after you move your piece right, you continue. So this, I think in the regular Joe calls this a sequential decision-making problem. And in this situation, right, we're making continuous moves. It's not, you're training your agent to play the entire game of Tetris, not individual steps. When this relates back to fully and partially observable, then, well, in the episodic, if you considered Tetris to be episodic, here's my snapshot, well then it is fully observable because I see the next piece that I'm going to get, right? Even though you can't see all of the future pieces, it's a separate problem. My problem right now is just tell me the exact best move based on the probabilities and what I think may come out, right? So you're reasoning over the individual snapshot episode of the game. However, I think normally, right, in the sequential sense, we consider Tetris to be partially observable because we can't see the pieces that are coming in the future. But that depends very much on the way you're viewing the problem. If we know what that random chance is, then I think you could consider this fully observable. I think I'll put I'll put it down as both. I think it's partially observable with an asterisk of whether or not you know the actual moves. But yeah, so you're mostly seeing the problem, but the part of the problem that's hidden from you, right, is the pieces that will come, the pieces that will follow after the next. Of course, Tetris is single agent. More often than not, right, you're just considering this to be like you are a controller, you control the current piece, the current move, the crane, or whatever else you want to call it. You're the player clicking the buttons. There's a worldview where like you treat yourself as, well, you treat each of the individual pieces as their own agents, but I think that's a bit of a long shot. Okay, dynamic versus static. This is, I would say it's a static problem, right? Because when we're reasoning, it's the current time step. So nothing changes until the next time step. So if you're writing something to play Tetris and it can reason and make a decision well before the next time step ever ticks, then it's a static problem. However, if you're tasking a robot with, it's got times just ticking the whole time while we're planning, right, and we have to make decisions quickly, well then it becomes, I should just stop doing asterisks and just write both. Then it's a dynamic problem in that situation, right? If you don't have infinite time to discuss your move, well, I might have come up with a plan. I want to turn right, but then, oops, time's already, but when I was still planning that, time has ticked, my block actually hit the bottom, and I can no longer do the move that I would like to do. And then in that case, this would be a dynamic environment. Okay, so in terms of deterministic and stochastic, well, this is finally an easy one. It's obviously deterministic. If I tell the piece to move right, it'll move right. There's no randomness built into the actions that I'm doing. Students often get very confused. They argue, well, it's stochastic, right? Because there's randomness built into the world. It's randomness into what piece will exist in the future. That is not what deterministic versus stochastic is actually describing. This is talking about the effects of your actions, the operators and the things that you can do in the world. So next then we have discrete versus continuous. Well, this will be, I think, depending on, again, how you model the problem, I think you'd consider most games of Tetris to be discrete. There's discrete time steps, there's discrete locations. Maybe there are versions of the problem that you could define that is this continuous movement and things like that, continuous time. But I think usually we try to describe this in terms of like the state space, and you would consider the state space to be discrete time steps and discrete locations. Finally then, there is known versus unknown. Well, you know the rules of Tetris. It's known, right? You know the actions available to you, you know their effects, you know the rules of the world. You know the probabilities. In a standard sense, we know the rules of the world. Tetris is a known problem. Okay, so there's a whole lot of, there's like, obviously there's asterisks and I can write multiple down. It's because this is just trying to get you into the idea of discussing these problems in terms of standard terminology. Problems don't always fit perfectly nicely into one category. You were the one in control of this, right? When you go to implement the problem and to solve the problem, well, at some point you're going to have to make decisions about these facts, about which version of the problem you're solving, and then that will inform the way that you want to actually try to tackle it and to solve it. So thanks for watching, and I'll see you in the next videos where we start to talk about some of the harder environments and how we're going to go about solving it. Cheers.